Here's an interesting kinematics slash dynamics problem with a bit of optimization built into it that was at the Romanian Physics Olympiad, well, I should say the Romanian National Physics Olympiad back in 2018. This was given to ninth graders and it was problem 2A. And if you have questions that you'd like to see me do on the channel from previous years or anything that's remotely similar to this, let me know down in the comments. So as usual, let's read the question and let's try to understand how to approach it. So this is labeled as Galileo's problem because this was apparently in one of Galileo's books way back in the day. So we have that a small ring descends without initial velocity along a smooth rod labeled MN, like in this figure here. Point M, which is where the ring starts from, is on the line AMOB that you can clearly see here, and this line is inclined at an angle alpha relative to the horizontal. And the other point, which is point N, is sitting on the straight horizontal line. Point O is the point of intersection of the two lines, that's obvious, and the distance ON, labeled as small l, is considered to be known. And part A is asking at which distance OM equals to x, so basically we have to find what's the value of x, such that the ring will reach point N in the smallest amount of time. So let's try to understand this, let's try to summarize it. So point M is fixed somewhere on line AB. We don't exactly know where because that is given by the x coordinate. And once we fix point M on that line, we release a ring. I just realized that those are Romanian words. So basically this means ring, and this is referring to the bar, MN. Anyway, so we're trying to fix point M somewhere on that line AB so that when we release the ring from point M, it will slide down the bar in the smallest amount of time. So let's try to solve it. So I'm going to try to draw this triangle here. So I'm gonna draw this triangle a bit more zoomed in because this is literally the only part of the problem that we're interested in. So we've got the horizontal line and then we have the bar, which is like this, and then we have the other line, which is our x. So let's draw it like this. Okay, and let's label a couple of points. So this is N, this is M, this is x, and this is the length small l that we know. Okay, so this angle is alpha, and this angle is given to us, and so is this length. So the only three things that we know are, so let's write it here. So the things that we know are alpha, L, and G, right? Yeah, this is also mentioned in part B that local gravitational acceleration G is considered to be known or given. Okay, and the ring is released from M and it's sliding down the bar all the way to N. So the first thing that we should try to find is the acceleration of the ring, because the acceleration together with the length of the bar is going to give us the time. So we have an angle here which we're going to call theta, and as the ring is sliding down, its acceleration, and I don't really want to spend time proving this, but the acceleration is going to be equal to g multiplied by sine of theta, right? And you can find this quite easily by considering that bar mn to be an incline, and it is acting as an incline, and the acceleration therefore is g sine theta. The only problem with that is that we don't know what theta is, and what's more is that theta depends on x, which is our variable. So in a way, theta is also a variable. Now, we don't want to have too many variables. Ideally, we just want to have one, which is our x value. So everything else that we don't know, including theta, we want to express in terms of x. So let's first think about this time that we have to find. So we know that this ring is sliding from m to n, so it doesn't have any initial velocity or anything like that. So we can write that mn is equal to 1/2 times the acceleration times t squared, right? So this comes from the Suvet equations, or however we want to call them. So we can rearrange this to find the time, or time squared. So this is 2 times mn over a. Okay, so that's the time which we have to minimize. Now, the only problem is that we've got two unknowns. We have mn and we have the acceleration, which in turn depends on the angle. So let's rewrite this. So we've got t squared is 2 times mn divided by a, and this is 2 mn over, so instead of a we write g sine theta. So I've got two things to worry about. There's mn and then there's theta. So let's treat them separately, and let's try to find mn in terms of x, hopefully. Now, if you look at this triangle, you can get mn using the cosine rule, right? So you can use the cosine rule, which is also called the generalized Pythagorean. So this is the square root of x squared. Let's call this point O as well. So it's x squared plus L squared, and then we have minus 2xl cosine of alpha, like this. So that's mn, which is great because now we expressed mn in terms of x. And everything else, like L and alpha, those are constant, so we don't really care about them. So that's sorted, at least part of it. So that's x squared plus L squared minus 2xl cosine of alpha. And then we have this theta to consider, which we don't know at this point, but to find theta, we can use the sine rule. So we can say that sine theta over x is equal to sine alpha over mn. Right? This is just the basic sine rule that's used in this MON triangle. And then we can rearrange for sine theta. So sine theta is equal to sine alpha times x over mn. So instead of sine theta, I'm going to write this, which is sine alpha and then x over mn. Now we know what mn is already, right? Mn is the same as what we have here. So let's write that t squared is 2, and then we have square root of x squared plus L squared minus 2xl cos alpha over g. I just realized I made a small mistake here. So this should be g sine alpha, and that's x over mn. So that's g sine alpha x over, and then we have that square root, which is squared plus L squared minus 2xl cos alpha. So this gives us 2 over g sine alpha, and then we have x squared plus L squared minus 2xl cos alpha, everything divided by x. Okay, and we're gonna get 2 over g sine alpha, and then I think it's easier if we try to divide. So this is gonna give us x plus L squared over X minus 2L cos alpha. Okay, so we've expressed time, or time squared, in terms of X. So the only part which contains X in our expression on the right hand side is what I just circled in yellow, and this is the only thing that we have to minimize. So let's call this f of x. Yeah, and let's try to minimize f of x. Now you can actually do this in a few ways. If you want, you can do some completing the square stuff, but I think at this point it's probably worth knowing some basic differentiation just to reduce the amount of headache that you get from this. So I'm gonna say that f of x is x plus L squared by x, and we're gonna try to find the stationary points. So we do df by dx, which is gonna give us 1 minus L squared over x squared, and this is gonna be equal to 0, right? So x squared is equal to L squared, and the only valid stationary point is x is equal to L. Yeah, we don't take the negative because this is a physics problem. We're not doing pure maths here. So x is equal to L is actually, it will actually give us the minimum. So this gives us the minimum. And you can convince yourself that this is a minimum and not a maximum or a point of inflection, because if you differentiate f again, so if you do, if you find the second derivative, like this, this is going to equal, let's see, so we have, I think, L squared over x to the 4 times 2x, which is 2L squared over x cubed, which is positive. So yeah, if this is positive, then when you plug in the stationary point, it's also positive, so this is a minimum. Okay, so we found the value of x, which minimizes the time in which the ring can slide from point M to point N. So we found x, so all we have to do now to find the time itself is just take this x and plug it back in here, which is going to give us that t squared equals, so we have 2 over g sine alpha, and then we've got in brackets we have L plus L squared over L minus 2L cosine of alpha, which is t squared is equal to 2 over g sine alpha. So we can cancel out an L, and this is going to give us 2L times 1 minus cos alpha, which gives us that t squared is 4L over g, and I'm going to combine those trig terms together like this. Okay. So we can actually leave it like this. The problem is basically solved at this point. So we've got a time, a minimum time I should say, which is equal to this, and that corresponds to an x value equals to L. So what does this actually mean? Well, it means that point M should be placed in such way that those sides of the triangle are going to be the same. So in other words, minimum time is achieved when this MON triangle is isosceles, which is interesting. And that gives us this time, which we can actually simplify a bit more. And the way we can do that is we use the double angle identities. So we say that sine squared of alpha over 2 is 1 minus cosine of alpha divided by 2. So 1 minus cosine of alpha is 2 sine squared of alpha over 2, and also this denominator, the sine alpha, this can be written as 2 sine alpha over 2 cosine of alpha over 2, which will give us that t squared is 4l over g. So on top we have 2 sine squared of alpha over 2, and on the bottom we have 2 sine alpha over 2 cosine of alpha over 2. We can cancel out a sine like this. We can cancel out the 2's. So we end up with t squared equals 4l over g, and then we have sine over cosine, which is tan of alpha over 2, which is, yeah, a bit more simplified, I guess. So the time is going to be equal to 2 square root of l over g tan alpha over 2, and that's the time. That's the minimum time, which again corresponds to this triangle MNO being isosceles with the unknown value, with the unknown length x being equal to L itself. And that's the end of the question.